did that as if there were no more questions. Any other questions? All right. I did something with the stylus there, just. We last left off, we were dealing with an object that was spinning around a tube. And we ended up with an equation that was very difficult to solve. Not impossible, but difficult. All right, so it's hanging at some angle theta. And so we broke, and the force is acting on it. I guess that is a string. It's part of the tube, or going through a tube, and hanging, another mass hanging down here. Did I label these A and B, or 1 and 2, or? A and B. A and B? A and B. Okay. So the forces acting on A is we had the weight of A acting down, and we had the tension acting up. And then for B, we had tension acting up, and the weight of B acting down. We established the direction of acceleration for the weight of A is that way. And I'm doing a different color because the A there is not part of the force diagram. It is just a separate note. So I set up my coordinate system. And I don't remember, did I do up positive, down positive? What was it?
We did down positive.
Down positive. And for this one, do we just keep the same convention, down positive?
No, up positive.
Up here, we make it up positive. I'll call that Jason A, I said A, and Jason B. We broke the forces up there. And so I had tension times the cosine of theta acting towards the middle. Tension times the sine of theta acting up. Weight of A acting down. Nothing to break up there. Then we came up with the equations of motion. Ft cosine theta is equal to mv squared over r. Ft sine theta minus wa equals 0. And Ft keeping with the convention, wa minus Ft sine theta equals 0, and then Ft minus Wb equals 0. That should match the equations that we had.
Yes.
All right. Substitution, I already made the substitution there, but let's do the weight substitution. So if Ft cosine theta is equal to mv squared over r, m sub ag minus Ft sine theta equals 0, and Ft equals m sub bg. I think that's sort of where we left off.
Yes.
So, we are trying to solve for the speed. How do you solve for speed?
Distance over time. Distance over time.
Okay, except we don't have time. Now, there's a lab that you're going to do where you'll find speed doing distance over time, but we're sort of working at it from a different angle today.
You said before we left it was B equals R times alpha. Or not omega.
Alpha is the fish.
So not
Omega looks like a W.
Yeah, omega.
Okay.
Yeah.
All right. Before we actually do that, we will get to that, definitely. First, recognize I do have a formula for tension here. It's not independent, so that's why it doesn't go during the substitution phase, but during the solving phase, I do have a formula here for tension, and I can make that substitution. So my first equation becomes mBg cosine theta is equal to mv squared over r, that's m sub a. And that second equation there, I get m sub ag equals, bringing the second term over to the other side, mbg sine of theta. The masses I would know. G, if I know the planet I'm on, I can come up with a pretty decent value for that. R, well, I don't exactly know R. If I were measuring this, I could easily measure that length right there, and I'll just label that length L. But R is this distance right here. So I need to figure out what R is. So R is an unknown, V is an unknown, and theta is an unknown. Because as I swing it, try that one again. So as I swing it, if I have a small speed, I've got a large angle, but as I increase the speed, theta will get smaller. So my speed is going to have an issue. Basically, I've got two equations and three unknowns. So I need one other relationship here in order to solve it. I need three independent equations if I'm solving for three unknowns. So what is the third equation? Well, I know that the force of tension is along this line right here. I also know that the length of the string is along that line right there. I have a physical relationship between R, L, and theta, and then I've got a force relationship between tension and theta. But based upon this, what is the relationship between R, theta, and L? I can draw it separately if I do R, L, and theta. That's what I'm working with. And it's a trig function. Cosine, is that it? Cosine of theta is R over L? Is that what you're going with?
It has all of them.
Yeah, and that's what we're looking at here. So I know that R is equal to L cosine theta. So my first equation there with that, so let me write that in there, that cosine of theta is equal to R over L. If I solve for R, I can plug into here, so this equation now becomes mBg cosine theta is equal to m sub a v squared over L cosine theta. And then I have mag, well, actually, my g's cancel out there. So ma is equal to mb sine theta. Now what? Well, the unknowns are v and theta. Okay.
We have the masses. We have the masses. We can solve for theta.
All right, so how do you solve it? So what is theta equal?
Inverse sine of mass A over mass B.
I now have theta, I can now plug into my equation up there, solve for V. So V is equal to the square root of MB over MA times G L cosine squared of theta, which is the arc sine of MA over MB. It's as simple as that. Let's just do a quick blanket check. Let's come up with some answers here. So let us set up, I need mass A to be smaller than mass B. If there's no friction, if mass A is bigger, then mass A is just gonna fall and mass B is gonna go up, and no matter how much I swing it, that's not gonna change that. So put mass A at 5 kilograms, mass B at 20 kilograms, and L we'll put at 3 meters. Obviously, not necessarily realistic numbers if a person is doing this. So we can figure out the angle from that. I probably don't want to use that on the electronic board. So my angle is the arc sine of mass A over mass B, so that puts us at equal to the arc sine of 5 over 20, which is
14.48 degrees.
okay. So that's our angle right there. So my speed would be, given that length of rope and that mass difference right there, or mass ratio, the square root of MB over MA, so 4 times 9.8 times 3 cosine squared of 14.48 degrees. So what do we get as the speed? All right, so that's gonna, so somewhere around 8. The answer is,
10.5.
what is it?
10.5.
10.5? Okay. Units?
Huh?
Units? Question mark?
Meters per second. It's possible.
Technically, it's the speed. All right, so 10.5 meters per second, so a little over 20 miles an hour. If that's the case, if it is indeed going to 10.5 meters per second, how long does it take to go all the way around? In other words, what is the period of rotation? Period is if you have something that's have repetitive motion, period is how long it takes for each cycle to happen once, or the time for one cycle of repetitive cycles. So if this thing is spinning around repeatedly, how long does it take to go around once? If I ask for the period, that is a time. The symbol for period is a capital T, which is one of the reasons I don't use capital T for tension. Actually, that is the reason, not just one of them. That's all repetitive stuff. Well, let's go back to the, how do you find speed? Was it, Kevin, did you say, somebody said,
Speed over, distance over time.
yep, that's the one. All right, so speed is distance divided by time. And I'm talking about one rotation, so that time is gonna be the period. What is the distance? I have this thing traveling in a circle. What is the distance called?
The circumference,
Yeah, and the formula for circumference?
2 pi r.
And there's my radius. I have a formula right over here. L times the cosine of that angle. So R is equal to L cosine theta, which is 3 meters times the cosine of 14.48 degrees. 2.5?
9
9.
meters.
And I will say, that's one of the few times when I asked for units where the student didn't look down at the calculator or something like that, so I appreciate that. I understand the impulse to look down at the calculator, because that's where you just got the numeric answer. But I haven't yet to see a calculator that gives units. I'm sure they exist somewhere. All right, so I now know R. I know everything except for the period. So I have 10.5 is equal to 2 pi times 2.9 divided by my period. And so solving for the period, 2 pi times 2.9 divided by 10.5. And we end up with 1 point. Sorry, what is it? 1.74?
Seconds.
Because it's time. Now, yesterday, what was that equation we ended with?
The V equals pi omega.
Yeah. So I have something very similar to that right here, except I've got 2 pi r over t. So if I just sort of rearrange it a little bit, put parentheses like that, do 2 pi over t times r, well, sure be convenient if that's omega. That's supposed to be an omega, not a w. And so the speed is equal to r times the angular speed, which indeed is 2 pi over the period. Now, angular speed in general is the change in the angle over the change in time. And if I'm talking about one revolution, the change in the angle is 2 pi radians. So, and if I'm talking about one revolution, the time it takes is the period. So given that, this right now, I know my centripetal acceleration, the magnitude, is equal to v squared over r. Well, if I plug in my formulas right there, that r omega, so I got r omega squared over r, which is r squared omega squared over r. And the r's cancel out, and r cancels out. And so I'm left with r omega squared. So I have a second formula I could use for centripetal acceleration. I can use v squared over r or r omega squared. Either one is acceptable. Which one you use depends upon what you're trying to find or what you're given. If you try one and it doesn't work out particularly well, try the other one. If that doesn't work out particularly well, then it might be a difficult problem or there's mistakes somewhere. Questions up to here? So I have MBG cosine theta is equal to mass mv squared over r, that's mass of A. All right, that was the equation that I had up on the board, just right there. It actually is convenient if I use omega squared, the r omega squared for centripetal acceleration, so MBG cosine theta is equal to MA r omega squared. Actually, I'm going to write that in the opposite order, omega squared r. Not real crucial, I was going to flip it in a second if I hadn't done it there. I know that r is L cosine theta. So I have MBG cosine theta is equal to MA omega squared L cosine theta. And my thetas go away because I have a common term. So I have a much simpler relationship to work with. MBG is equal to MA omega squared L. So the weight of my hanging mass is equal to the mass of the swinging mass times omega squared L. It's as if we were dealing with a following situation. I still have mass B down here. It's as if mass A is swinging, that's L. It basically is this situation. If I'm using that as it ends up, the omega squared times that length right there. And in the 110 version of the lab that you'll eventually do,